All right, here we are. So let's get it together here. I'm going to open up all of our notes. Now we were just about done with 4C. I think there's just one or two more examples we needed to look at, and then we can start 4D, and then we can move into 5. So let's go get those open. Maybe over the weekend. That sounds good. I certainly will be able to do it this weekend. I'll be free to do all of the grading, so I should have it ready by then. All right. Anyway, all right. So let's get these open. Okay, you're welcome. For C, just a few more examples. And then for D, we haven't started yet. And then we'll be ready for 5. Wow, we're zooming along here. And these are all on Moodle. And so let's get back to C. Okay, so we've been using L'Hopital's rule. And if you recall, L'Hopital's rule is going to be used in cases when direct substitution leaves us with a ratio of either 0/0 or possibly infinity over infinity. It's really only meant for those two cases. And if that is what we get with direct substitution, instead of giving up, what we can do is just say, oh, wait a minute. What we can do is calculate the derivative of the numerator and the denominator and then try again. And hopefully it works this time. If not, there are other techniques that we can try, but often that's going to get us our result. Okay, so again, it's just for the 0/0 and infinity over infinity cases. Now, sometimes, having said that though, we can rearrange our problem to force it to be 0/0 or infinity over infinity. So in other words, you'll see some of these examples, even if it isn't already in the right form, sometimes we can rearrange the expression algebraically so that it is now something that we can apply L'Hopital's rule to. So we've done most of these already. Let's see, where did we leave off? And in all of these cases, since you have Symbolab available to you, if you're not sure what the limit should be or could be, it's really very helpful to be able to look at the graph, because then you should get a better sense of what the limit is supposed to be before you actually go ahead and calculate it yourself. But I think it's helpful to know what it's supposed to look like before you actually do all the calculations. So anyway, now this is where we left off, the other indeterminate forms. So sometimes you get these other crazy cases where clearly this is not a number that we can call the limit. 0 times infinity, infinity minus infinity, infinity to the 0 power, 0 to the 0. In these cases, your strategy often is to try to rearrange it algebraically to convert it into the form 0/0, or maybe infinity over infinity, and then you can go ahead and use L'Hopital. You can't use it in these other cases, but you may be able to rearrange everything to force it into those two forms. So we did some of these already, if I remember correctly, like this one, for example, 0 times infinity. This was a bizarre case, that's for sure. Here's the graph. And so if we were to plug infinity directly into the expression you're seeing here, you'll end up with infinity times 0 or 0 times infinity, which means we're not going to be able to use L'Hopital's rule, but we might be able to rearrange it and force it into that format. By the way, just as a quick reminder, anytime we take the limit of x as x to the n rather, as x goes to infinity, what's happening is that x to the n is getting extremely large, and eventually, I mean, we define the limit to be infinity. On the other hand, if it's 1 over x to the n, then what's happening is that we're getting a denominator which is getting extremely large. And so 1 over an extremely large denominator is converging to 0. Okay, so we will need that in several of these cases. Now, like here, what I did was from before, this was not a very complicated transition. I just multiplied the numerator by 3x squared. Now, the advantage of doing this, though, and this is the technique that we want to use for these types of cases, it may be possible to divide the numerator and the denominator by a power of x that reduces this to a form that can then be handled with L'Hopital's rule. But we may not, it may not work the first time. In other words, you can try different exponents until you find one that works. Like here, for example, if we try x squared, what ends up happening is that we don't need L'Hopital at all, because in the numerator we have 1. In the denominator, we have 1 plus 1 over x squared. And as we just saw a little while ago, the limit of 1 over x squared is going to be 0. Because again, the denominator is getting very large. So all of a sudden, we're left with 3 times 1 over 1 plus 0, which is just 3. So the cleverness here came about by that division by x squared. That's what made it possible to reduce this to something manageable. And we did, in fact, end up with 3. Now, this one was 3x squared over x squared plus 1. We're going to try a similar one where the denominator, instead of x squared plus 1, it's just x plus 1. Now, if you did the same approach you did before, dividing the numerator and the denominator by x squared, you'll end up with 3 over 0 after direct substitution, which is exactly what we don't want. 3 over 0 isn't good enough. It has to be 0 over 0 to use L'Hopital's rule. So what can we do instead? Well, this time, why don't we try dividing by x, not x squared, but x. So what does that get us? Okay, in the numerator, we have x. By the way, I've moved the 3. Whenever there's a constant in a limit, you can just essentially move it outside. In other words, what you're seeing here is equivalent to this. You don't have to. It's just sometimes it's more convenient just because you might be trying a particular strategy, and moving the constant outside might make it easier to see what strategy you're supposed to use. Okay, so here that's what's happened. We divide it by the x. Now in the numerator, we still have x. So we're going to have an infinity in the numerator. In the denominator, we have 1 plus 0. So, oh, bad luck. We have infinity over 0. And sorry, infinity over 1 times 3. When we're dealing with infinity, multiplying infinity by a constant, adding a constant to it, subtracting, none of those affect the result. In other words, we can just call it infinity. It doesn't make any difference if it's infinity or 3 infinity. It's still infinity. Now, this means that we did not choose wisely. We can't really do anything with this. We simply say the limit is infinity, and that's the end of it. We can't use L'Hopital or anything to simplify it. The limit is simply defined to be infinity. Now, that usually means that there's an asymptote of some kind. So if you look at this graph, let me just go find. Oh, where's my? Oh, here it is. Here it is. Oh, there it is. I think that's left over from. No, almost. 3x squared over x plus 1. All right, let's take a look at this. Okay, so you can see there are a couple of asymptotes. And wow, this is an interesting one. By the way, don't forget this, the Symbolab is capable of doing limits. So let's see what Symbolab has to say about this. So they got the same thing we did, infinity. And so here's the strategy that they employed. They divided everything by x like we did. They factored out the 3. And in the numerator, we ended up with infinity. In the denominator, 1 plus 0. And that's what we wound up with. How do you like that? Okay, well, that's that. And then what about this one? Oh, all right. So this time, because we have x cubed in the denominator, let's go ahead and try to divide everything by x cubed and see what happens. And by the way, before we even do that, just note that if you directly substitute, well, actually, in this case, we could have directly substituted, but let's just do the division. Dividing by x cubed means we're going to wind up with 1 over x in the numerator. In the denominator, we have 1 plus 1 over x cubed. And now, both of these, when we have direct substitution, will give me a 0. So I got 3, remember, there's still 3 here, times 0 over 1 plus 0, which is the same as 3 times 0 over 1, which means we just end up with 0. All right, why don't we take a look at this one? I think it's a good idea. 3x squared over x cubed plus 1. Just to look at the graph. Oh, see, you don't usually see them get wrinkled like that. But you can see from here, as we keep increasing x, it's getting closer and closer to the horizontal axis. So here, the limit is 0. Now, here's an interesting one. Now, remember, logs are a little tricky because the way the log function works, as we approach from the right, you can see that the vertical axis is an asymptote. Okay, but here we don't have, then that's for log x. Here we have x log x. And we cannot approach from the left, okay, because the limit, the log rather, is only defined, the domain is 0 up to infinity, not including 0. So in other words, the function is undefined for values below 0. So in this case, we can only approach from the right. So what should we do? Now, if we plug in that number, log 0 is undefined. We're going to call that negative infinity because, as you can see, the function is shrinking very dramatically and never quite reaches negative infinity. This is not going to allow us to use L'Hopital's rule. We just have a mess. Oh, there it is. Okay. So here's a possibility. Let's try this. Let's rewrite this as log x divided by 1 over x. How does that help? Oh, now here's the, well, all right, here's the interesting part. The L'Hopital's rule even though it says, you know, in the book, 0 over 0, infinity over infinity, I think they forgot to mention this, but that means you're also allowed to use it when you have negative infinity over infinity, or possibly infinity over negative infinity. So the fact that there's a negative there means we're good. We can use L'Hopital's rule. Now, that still doesn't guarantee we'll find a result, but it's much more likely. It's kind of unusual that L'Hopital's rule doesn't provide us with a result. It can happen, but it's kind of unusual. So you might recall that what we're going to do is take the derivative of the numerator and the denominator. And don't forget that the derivative of log x is very simply 1 over x. Now, 1 over x is x to the minus 1 power. And so the derivative of that is minus x to the minus 2 power. Or if you prefer, so that means when we are done, now, of course, we want to simplify that. And when we do, so let's take a look at this. 1 over x is x to the minus 1. Here, what I've done is I've rewritten it as x to the minus 1 over minus x to the minus 2. So when you have something like this, so what you can do is subtract the exponents. Okay, there we go. So you've got the limit of minus x to the first power. Any way you look at it, it's just 0. Okay, and so once again, why don't we look at this graph? X log x. Let's see what that looks like. Ah, well, there you go. You can see that we're approaching 0. And from the right. Okay, so in other words, you have to imagine that we're going from the very large x's to the small x's, and we're getting very, very close to this hole here. And so that is our limit right there, the 0. Okay. Now, some of these cases can get very bizarre. Like here for a difference, for example, if you have a result of infinity minus infinity, well, then you have to take a look at the individual functions and decide which ones are increasing the most rapidly as x approaches infinity. That will help us decide if the function is approaching positive or negative infinity. So here's an example. We're going to take the difference between two polynomials. And why don't we look at this graph? It looks like a pretty standard polynomial. There shouldn't be any bizarre features to it, but you never know. You should never say never. Y equals 3x cubed minus 3x squared minus 5 Huh. That's pretty normal. I mean, it's a cubic function, so it has that standard cubic shape. So it looks though as x increases to approaches infinity, though, the function continues to increase forever. So direct substitution gives us infinity. Infinity minus 5. Oh, now wait a minute. I just realized something. If you look at this graph carefully, how do you like that? The limit is not infinity, it's actually 5. Okay, I'll tell you what, let's throw this into Symbolab. Oh no, it is infinity. Okay, that's good. That means I have a typo in here somewhere. Yeah, because I've got it. Let's see, here's negative infinity. Oh, I know what happened. What did happen? Hold on a second. Oh my God. You know what I think happened? This is a different example. Oh, Jesus. Okay. I just realized now, I thought there was a problem. No, I was looking, unfortunately, at a different example. So let's go back and try this one. 3x cubed minus 3. Yeah, so this one is fine. The limit ends up being infinity. Okay, so yeah, exactly. So in other words, it just keeps going up and up forever. Fine. But direct substitution gives us this mess. And so what they're basically saying is, listen, since 3x cubed is increasing more rapidly than 3x squared, that will dominate the subtraction of 3x squared. So the function will eventually converge to infinity. So that's what we have here. But then this next one is 3x squared minus g of x, which is 3x squared plus 5. So this is different because when you subtract them, you'll see that you just wind up with negative 5. So of course the limit is negative 5 because it's a limit of a constant. Okay, so in other words, in spite of the way it looks, this is simply the limit of negative 5. Then, now this is the case that I was concerned about. 3x squared plus 5. So now we're looking at this one. Let's take a look at the graph. So this one actually is negative infinity. So let's look at the graph and see why. Okay, well, there you go. You can see what's happening here. Yeah, I mean, it's just a standard parabola. It's just written in a slightly strange way. We typically you would express this as this. So it'd be easier to see right away that this is clearly a parabola that's facing downward. And so that's why the limit has to be negative infinity, because as x keeps increasing, clearly the function keeps decreasing and will eventually go to negative infinity. So in other words, and what they're saying, you don't even need the graph because 3x is a linear function, which is increasing more slowly than 3x squared. So you're subtracting a function that's getting bigger very quickly from a function that's not changing very as much. So the net result would have to be a negative infinity. Now, here's an interesting one. Infinity raised to the 0 power. Whenever there's an exponent, and you need to clean it up, so to speak, basically your strategy, your first thing should be to think about logarithms. This is where logarithms are so helpful, because what they do is they basically eliminate the exponent. Okay, the way they're written, we have, for example, y equals f of x raised to the g of x power. So what we can do is basically take the limit of a log, and if we're going to do it that way, we're typically will end up with a solution which is e raised to some power. So let's take a look at an example. Like look at this one. The limit of x raised to the 1 over x power as x goes to infinity. So first, let's take a look at the graph. I'm dying to see this one. Okay. Wow, now that's weird. Well, you can see there is an asymptote here at 1. Okay. And the function only starts not exactly at 0. The domain is 0 up to infinity, not including the 0. Right, as it shows here. So the limit, let's see, we're going to start by letting y represent x to the 1 over x power. The log of x to the 1 over x power is 1 over x log x, or log x over x. So just as a reminder, so when you have something like that, log of x to the n power, you can rewrite it simply as n log x. Okay, so that's what happened here. So we've got log x over x. But remember, this is not the original function. This is the log of y. So remember, if we define y as x to the 1 over x power, then the log of y is log x to the 1 over x. So that's what this is. So what we're actually doing here is we're not taking the limit of y now. We're taking the limit of log y. So let's not forget about that, because that'll affect the results. So this is the limit as x goes to infinity of log x over x. Now, direct substitution, as we've already seen, gives negative infinity over infinity, which means now we can use L'Hopital's rule. So of course, that means we're taking the derivative of the numerator and the denominator. And that's a very interesting case. The log of x d log x is simply 1 over x, as we've seen. Down here, it's just dx over dx, which is just 1. So we have this expression. Now, we've already seen 2. As far as the numerator is concerned, Direct substitution gives you 0. The denominator is just 1, it's a constant. So that means that the limit, not of y, but log y, is 0. So how does that help us? All right, let's find out. So if the log of 0, the log of y equals 0, that means e to the log y equals e to the 0. So we actually end up with a limit of 1. But here's the thing, though. You had to be careful with that logarithm. In other words, it would be easy to forget that we transformed it into a logarithm. And then you might have accidentally said, oh, well, look at this. The limit is 0. No, the limit of the log is 0. The limit of y, the original function, is therefore 1. Okay. So again, let's just let Symbolab do its thing. So it is 1. And they're offering to show you. Now, looks like they're doing it a little differently. They're rewriting x to the 1 over x as e to the 1 over x log x. I don't know. I think ours is better. A little cleaner, but we end up with the same result. So anyway, so now we're done with 4C. So 4D is a very, very interesting topic. You know what it reminds me of? All right, well, let's just think about this for a second. Suppose you were told that the sine of 90 is 1. Okay. Let me just confirm that. I used to have all these basic trig functions memorized, but yeah, not okay. What that implies is that the arc sine is 90. So you're basically reversing this operation. Oh, I almost forgot. You know, I'm getting so used to PowerPoint. In Word, there's actually a command up here that lets you do exponents directly. Okay, so in other words, the sine of 90 is 1. The arc sine of 1 is 90. Well, we can do something similar with derivatives. It turns out, let's say, for example, that our function is let's try. X cubed. Well, what we're going to do in this section is essentially work this process backwards. Normally, we start with a function and we take the derivative. What if instead we wanted to know this? I'm trying to word this in the clearest way I can. So in other words, we're essentially working it backwards, just like we did here. We're reversing the direction of the calculations. And this function, well, we know that it is in fact x cubed. We're going to apply a special notation here. You notice how it's a capital F. This is referred to as, or it has two possible equivalent names. It can either be called the antiderivative or integral of f of x. Well, anyway, so this is where we're headed. So what we're effectively doing is reversing the derivative process. We're starting with the actual derivative and working our way backwards to the original function, which will be from now on called either the antiderivative or the integral of our derivative. Oh, actually, yeah, okay. No, it should be good. So let's take a look at this thing. So I just wanted to get you prepared for this because it's kind of different than what you're used to seeing. So antiderivatives. The antiderivative of a function f of x is the function whose derivative is x. So here's my another example. If f of x is 2x, the antiderivative, which we'll express like this, is x squared because f prime of x equals f of x. And so therefore f of x, capital F, is the antiderivative of f of x. Or in this case, we can say that x squared is the antiderivative of 2x. So, and it, I mean, you can clearly see that if I take x squared and take its derivative, I'll end up with 2x. So instead of going from x squared to 2x, we're starting with the 2x and working our way backwards to the x squared. We're saying, given the function we have, what must have been the original function that was differentiated to get us to this 2x. Okay, so just in more general terms, by the way, once we start doing this, you'll see it isn't that bad. It sounds very strange and bizarre at first, like a lot of concepts in math. But once we had a little practice, you'll say, oh, this isn't so bad. So capital F of x is the antiderivative of lower f of x, as long as derivative of f of x equals the original function f of x for all x in the domain of f of x. Okay. Now, there is one wrinkle to this. One unfortunate wrinkle. Well, I guess I shouldn't say unfortunate. This is something that we have to consider. What if we did this? Suppose that once again, our function f of x is 2x, and we're searching for an antiderivative. What about the case of f of x, capital F of x is x squared plus 3. Before it was f of x squared rather. Now we're trying out x squared plus 3 to see if maybe it could be an antiderivative of 2x. Now here's the tricky part. If that's our f of x, then f prime of x is also 2x. So as remember before, we claimed that our antiderivative was x squared. Oh no, what's going on here? Can they both be the antiderivative of 2x? And the answer is yes. And in fact, if you notice, if I try any other constant, oh no, all of them, no matter what the constant is, will be antiderivatives. So because there's always a potential for having a constant here, we're going to say that when we write this antiderivative, instead of writing it like this, we'll write it as x squared plus c, where c is a constant. Now, often we don't have enough information to figure out what that constant is. If we need that number, we can find it out. Oh, oops. No, right now, all you have to do is work on the midterm. Okay, yes, get that out of the way, and then we'll do some more assignments later on. Yeah, I don't want anything to distract you from the midterm. Oh, by the way, that reminds me of somebody in the class pointed out to me today that question number 7 turns out to be a lot messier than I anticipated. So what I'm going to do is give everybody full credit for question number 7, no matter what you write. Okay, I just forgot about that until right now. In fact, I think what I maybe want to do is post an announcement, because I don't want to forget about this. You'll look at it and say, oh my God, what's going on here? I guess I did not choose carefully with that one. And later on, if you want, we can go through and we'll look at Symbolab and see what it's telling us. But just for now, just be aware that question number 7, which seems, I mean, when you look at it, it looks pretty harmless. You're just being asked to do a domain and a range, but it turns out that the range is far more complicated than you might realize. Okay. I'm telling you, this week, technology has let me down more than usual. It's not cooperating. All right, I'll just have to remember to do it later. Just make a note of it somewhere that problem number 7, you're not responsible for. Okay, I'll try to get an announcement posted later when the website will condescend to let me do it. All right, so let's get back to what we were trying to do with the 4D, the antiderivative. So anyway, whenever we calculate an antiderivative, we're always going to add a c at the end to indicate the possibility that there's some constant there that we can't identify without further information. It's something we have to get used to. So in other words, you can see here that no matter what constant I pick here for this antiderivative, it will work because the derivative of x squared plus a constant is always going to be 2x. Okay, so with all that being said, why don't we try an example? So for the function f of x is 3x squared, what is the antiderivative of x, f of x? In other words, what function's derivative brings us back to 3x squared? Well, it just so happens, now by the way, for these few examples, basically, we're going to show you the actual antiderivatives. We'll see in chapter 5, well, actually later on in this chapter 2, a more formal approach to doing this. Right now, we're just trying to introduce the concept. So in other words, you might say, well, why did you choose x cubed? Well, because I've done this before and I've had practice, but we'll see pretty soon that there is a formal way of doing this. And there's a series of rules that we can use to help us identify these antiderivatives. But for now, it's enough to note that because the derivative of x cubed is 3x squared, it stands to reason that the antiderivative is x cubed plus that constant that I mentioned. And if you want to confirm it, of course, if you take the derivative here, you're going to get 3x squared using the power rule plus 0, or just 3x squared. So this proves that this is, in fact, the antiderivative of this. So again, think of it as working backwards. Instead of having a function and taking the derivative, we're essentially starting with a derivative and working it back to the antiderivative. Okay. So the next example will be the same thing. You'll say, well, wait a minute, how did you know that? Well, we will discover this as we move further into this chapter, but especially chapter 5, where we spend a lot of time with these techniques. Okay, so let's say we're looking for the antiderivative of 1 over x. Well, if you recall from earlier, the derivative of log x is 1 over x, and that's what we were looking for. So therefore, the antiderivative must be log x plus the constant, and that's because if I take the derivative, this is what I'll get. Now, by the way, there's always wrinkles, there's always complications. We have to be careful with logs. Remember, because of the way they're defined. What the problem here is that this result that I've just shown you only applies as long as x is positive. What would we have to do if x is negative? In other words, this x in the denominator right here, what if I have something like 1 over -3 or just any negative number? So what has to happen then is this. The antiderivative will change. It has to be log of -x, because that's going to give us -1 over -x, which again brings us back to x. So what we're going to do from now on is say that the antiderivative for 1 over x in order to incorporate both cases, instead of having a separate one for x is positive and x is negative, we're just going to do this. We're going to call it the log of absolute x. Okay, so in other words, instead of having log x, x greater than 0, we'll incorporate all of that, we'll consolidate it into just this. In fact, well, maybe what we could do here, I know that Symbolab can do antiderivatives. Let's go check that out. I've never attempted to do that. Look at this thing. How about doing what I tell you? Okay, ooh, I think it may have accidentally worked. All right, this is the announcement. I just want to, certain things you just want to do them before you forget. So this is the message. Question number 7 on the midterm will not be counted. So even if you write that the answer is happy face or something ridiculous, you'll still get the credit, okay? All right, good. So that's out of the way. So anyway, let's go back to the symbol. Now I know it has it. It's here somewhere. Oh, there's the implicit derivatives. I couldn't figure out where they were hiding. If anyone, by the way, if you want to practice with implicit differentiation, Symbolab is perfectly capable of doing it. I just didn't know where they kept it. So now, okay, by the way, we haven't gotten to this point yet, but there's a special symbol for antiderivatives, and that it's this thing. Supposedly, what happened here is that you know that the sigma is often used to represent summation. We'll see in chapter 5 that an integral or antiderivative is really nothing but an infinite sum. And so some people have suggested that the symbol just means you took the sigma and you sort of stretched it out a little, and we ended up with this. This will be the symbol we'll be seeing in chapter 5 for calculating integrals or antiderivatives. So what I'm going to do here, there's just, by the way, there's one more piece of information we need. So we're going to go for 1 over x. But in order to calculate, we need this extra term here, dx, the differential of x. Okay, so let's run it and see how it works. There it is. So it is, in fact, giving us the log of absolute x. And that's what it looks like. Which, by the way, well, I now have the paid version, which is, not very expensive. And wherever there are little hints here like this, I can look at them, always add a constant. Okay, so, all right, it's capable of doing this. Very nice. Here's a trig example. You might recall. So it stands to reason that the antiderivative of cosine x is sine x, but of course with the constant. Okay, and also don't forget this one. Now here's another interesting one. E to the x. That's one of our favorite functions to deal with because the derivative is crazy easy. You might recall that the derivative of e to the x is just e to the x. So what is the antiderivative of e to the x? Well, it's just e to the x plus the constant. Okay, so now we can sort of introduce the more formal representation of these problems. And that's the symbol I just mentioned. This is my symbol. Now, by the way, once we get past this point, from now on, we very rarely call these antiderivatives. Mathematicians tend to simply call them integrals. I don't know exactly why, but they both mean the same thing, but we'll typically use the term integrals from now on. And so this symbol represents, tells you to take an integral. And we'll see why later on, because what we're leading up to here is that these integrals, as I said, are infinite sums. And so here's what we're building up to. Imagine here's a curve of some kind. What if I want to know the area under that curve between these 2 points? Well, one strategy is to do this. What if I were to construct a series of rectangles reaching up to the curve, and I calculate the areas of all these rectangles and add them up? That would do the trick. But as we'll see later on, the accuracy of this approach depends on the width of those rectangles. As the rectangles get smaller, the approximation that we're doing here will get more accurate. And so what effectively ends up happening is that as we shrink up the widths of these rectangles, the sum converges to the actual area under the curve. And so when you take an integral, what you're actually doing is exactly that. You're taking an infinite sum of rectangles, which provides you with the area under that curve. So we're going to go through this and see the formal definition of integration, and we'll do it in terms of these rectangles. And then after that, we'll just use our rules. It's just kind of like with the derivatives. You might recall the formal method for calculating derivatives involves the limits. And we did that once or twice, but then from then on, we just use rules. The same thing will happen here. We're going to formally introduce the concept of integration and see what it really means. And it does involve limits. But then once we've gotten that done, we can go forward and just use formulas from that point on. Now, here's a formula that you'll find very, very helpful. If you're asked to take the integral of x to n, where n is anything but -1, that has its own separate rule. The integral is x to the n plus 1 over n plus 1. Now, we can prove it right now. What you're doing is using the power rule. Okay, because this was already in the denominator. This is the application of the power rule right here. These cancel out and you're left with x to the n. So that really opens up the doors to a lot of cases. So in other words, x to the n power, the integral is very simple and straightforward. So let's look at a couple of cases. And of course, never forget the c. What about x to the 4th power? What is its integral? Well, we're going to have, so n is 4. That means that here we have n plus 1, n plus 1. So I end up with x to the 5th over 5 plus c. And if you want to differentiate that, that's it. It works. How do you like that? Okay, so remember, as this works for every case except n equals 1. Wait a minute. Oh no, hold on. Sorry. I think I just realized, I think there's a typo here. No, that should have been -1. Oh, because you can see what's going to happen. You'll end up with division by 0. All right, I guess I'll have to fix this. Let me make a note of it. What is that, slide 13? Okay, I'll post the corrected version later on. That should have been -1, and you can see why again, because that would result in division by 0. So there's a separate rule for that case, but we will get to it later on. Okay, now, how about this one? X to the -2. -2 is fine. There's no problem there. N is -2. So here's n plus 1. N plus 1. So that's x to the -1 over -1, or just very simply -1 over x. Or if you want, you can leave it as -x minus 1. But it all means the same thing. Okay, so every case where you have just x with an exponent can be solved in this way, except for n equals -1. Now, obviously, there's many cases that we might encounter, but this will come up quite often. Here's a very simple case. What happens if I'm trying to take the integral of a constant? Well, the integral of k dx, k is the constant, is kx plus c. So why is that? Because d dx, we don't need to worry about the c. The derivative is just 0. So we can think of this as equivalent to k, and then the derivative of x, which you can think of that if you want as 1 times x to the first power, if you're applying the product rule, the power rule rather. So, wait a minute, what happened? Oh no, yes, that's right, that's right. So in other words, the derivative of this is k. Okay, so that's another one that's easy to remember. And again, you're likely to run into this. If you're integrating a polynomial, for example, you'll need this. And so here's a perfect example of the integral of 3. It's just 3x plus c. Now, here's an important, helpful hint. A constant can therefore be, quote, factored out. I don't know if that's the proper terminology of an integral. So in other words, this is where I'm trying to get at right here. These mean the same thing. So what you can do is bring the constants outside so that it's easier to spot the rule you're supposed to use. Okay, so now you look and say, oh, it's this one. And that's exactly what it is. So in other words, you're going to have x to the 6 over 6. The 4 is still right here. And of course, 4 over 6 is 2/3. So you end up with 2/3 x to the 6 plus c. Well, that wasn't so painful. Okay, now, before, remember when we were introduced to this rule, okay, where is it? Here it is. We did say that you may not use n equals -1 because that would be this. What do we do in that case? Well, we're about to find out. Okay, so that mystery is about to be resolved. Turns out that in that case, the integral is log absolute value of x. And then down here, you can see very simply, if we have the integral of e to the x dx, it ends up giving us e to the x plus c. So these are two very important ones. You'll see these all the time. Logarithms will pop up in many of these cases, as will e to the x. And later on, we'll see what to do with more complicated versions, like when you have e to the function of x or something like that. Then we have to work with the chain rule again. Over here, we're using the basic, relatively simple rules. And so like here's, for example, so we have this one. And like I said before, you can simply move that 4 outside. And then all of a sudden you realize, oh, wait a minute, it's this rule. I know that rule very well. But of course, don't forget the 4. And that's your final result. And that's all you have to do. Okay. Now, how about this one? Based on the similar reasoning, we can move the 5 outside and then, look what we have here. Just don't forget the 5. Okay, so you have 5. By the way, you don't have to worry about multiplying the 5 by the constant. I mean, theoretically, what you've got is this. But you know what? It doesn't matter if we call this C or 5C. So we typically just leave this at C because we don't know what that constant is anyway. So in other words, even though technically I have just multiplied the 5 by this constant, it makes no difference as far as our notation is concerned. We can just leave it as C. Okay, so okay, it looks like it's break time. And when we get back, we're going to look at a few more examples of these very basic cases. And then we can start looking at 5, where we start to more formally introduce what integrals are really telling us, what they mean and how they're derived. And we'll see that they do involve limits. Okay, so, but the setup is a little bit complicated. It involves, like I was showing you before, a series of rectangles, but we have to be very careful about the way we construct those rectangles. But anyway, so we'll save that for later. So right now we'll stop for a bit. When we come back, we'll look at some more cases here, and then we'll dive into chapter 5. All right, so let's try some of these trig integrals. Now, these are the basic ones. There's a few more complicated ones in the next slide, but we already know that the derivative of sine x is cosine x and vice versa. Let's just remind ourselves dx sine x is cosine x, and dx cosine x is negative sine x. So therefore, when you integrate the sine of x, you're going to end up with negative cosine x plus c, of course. And when you integrate cosine x dx, you'll end up with sine of x plus c. And again, you can always confirm these by taking their derivatives and making sure that they match up with the starting function. Okay, so like, for example, let's do this first one, d dx of negative cosine x. Now, since the derivative of this cosine is negative sine x, here we have negative cosine x. And so we're all set. Okay. And of course, you know, the second one is even easier. If we take the derivative here, we just brings us back to cosine x. Okay. Now, these next ones, I mean, we're not going to use them right now, but just for completeness sake, I've listed them here. And again, this is not all of them. This is just a handful of ones that you might encounter. But by the way, the book has an enormous list of just about every trig rule. I'm sorry, every integral rule that you could possibly imagine. And here we're just introducing the basic ones. So anyway, what else do we have? Oh, by the way, what we're going to see here too, though, is some of the algebraic properties that we can use to streamline our calculations of these integrals. So, but first, let's take a look at this one. So you can see now for the first time, we actually have a sum. And so, as you can probably guess, what we can do to maybe make it a little easier to see which rules we should be using is you can rewrite it as the integral of x dx plus the integral of e to the x dx. And once you've done that, you can look for whatever rules. Now, remember here is one of our favorite rules. And just remember that, of course, there's an implied one here. So remember, this one only fails to work at -1. So we're good. And over here, remember, we just saw this a little while ago. The integral of e to the x is just e to the x plus c. So therefore, we're going to wind up with, oops, what just happened here? I was hearing a weird noise coming out of the computer. What? Well, that makes me nervous. You know what it was? I was kind of leaning on that trackpad, which is never a good idea. But anyway, so here we'll have x. Now, actually, what you're really going to wind up with is this. But we can just combine the two constants. We don't need to treat them separately. Okay, so that would be the final result. So basically, this was a little bit different because we had a sum, but it was very easy to handle because all we have to do now is break up the integral into different components and then apply the rules individually. There's no rule, for example, for x plus e to the x, but it doesn't matter because if we split it up like this, we can see that there's a rule for each separate integral, and then we can go ahead and do it. All right, so this is what I was building up to. Right here is a list of a few things that we just want to remind ourselves. So don't forget that the capital F means we're taking an integral or antiderivative. So if you have the integral of a sum, you'll end up with the sum of the antiderivatives or integrals. If you have a difference, then we have the difference of the integrals or antiderivatives. And then also if there's a constant in your integral, you can essentially just factor it out. And then whatever the result is here, we multiply that by the k. So we end up with k times f of x, or capital F of x. And of course, as always, don't forget the constants. All right, so here's a nice little polynomial. We should have no trouble with this one at all. Let's try this one. What if we need the integral of this function? So you can see that we can clearly break this up into 4 separate integrals. And we just have to be careful about the signs. The second one is minus. Okay, so we have a negative sign here. So just write it out like this first. And then what you can do if you want to is you can move the constants outside of these integral signs. And then in each of these cases, the first 3 at least, you can use this rule. And in the last case, we can use this rule. Okay, so let's do that. So I've moved the constants outside. And then here, for example, x cubed becomes x to the 4th over 4, and then we still have the 5 there. Over here, x squared rather, when we integrate it, becomes x cubed over 3. So we multiply that by -7. And then here for x, it becomes x squared over 2. We still have the 3 here. And then the 4, plain 4 just becomes 4x. And then we, of course, still have the c. Okay, no. This next one will appear at first glance to be a bit of a nightmare, but not really. We can rearrange it in such a way that we can continue to use these same rules. Okay, so let's take a look. And again, don't panic when you see it. Oh my God, look at this thing. But no, here's what you have to remember. Just recall that this is equal to x to the 1/3 power. So we have x squared in the numerator plus 4x to the 1/3 over x. Now, clearly, we can divide. And what happens when we have 4x to the 1/3 over x? Well, remember, there's an implicit 1 here. So this second integral, well, actually, we can start like this. And then we can break it up into 2 separate integrals. And now, of course, we can use this rule on both of them, because in neither case is n equal to -1. All right, so let's see what that gets us. All right, so I've done that here. And wow, this one turned out to be a bit of a mess. So you've got remember what you're doing here. You're adding n1 to that n there. And when you add 1 to negative 2/3, you get 1/3. So dividing by 1/3 is the same as multiplying by 3. So that's why this turns into this. This one we've seen already, x becomes x squared over 2. And of course, at the end, we patch on the constant. So this is our final result. So while that looked like a very ugly problem, it turned out not to be such a bad one. So now, I just want to give you a little advance notice here. It turns out that while, yes, we did have an awful lot of rules with derivatives, I think you'll find that calculating integrals is going to prove to be even a bigger challenge because there's many more situations we can encounter. And there's quite a few techniques that we can introduce that helps us solve for the very complicated integrals. So here we're starting with the basics, but we'll see later on that this can get very challenging very quickly. But anyway, so that was 4D. This is meant to be just an introduction to the idea of integrals or antiderivatives. In chapter 5, we'll have a more formal introduction to the topic. And so let's take a look at this. So basically, the integral of a function can be used to calculate the area under a curve over a given interval AB, a given closed interval, I should say. And so I've drawn a little sketch. And by the way, I do want to mention something here. The integrals we calculated up to this point note in chapter 4, the integrals resulted in an expression, but not necessarily. Well, all right, let's put it this way, an algebraic expression. These integrals are formally known as indefinite integrals because they do not provide a numerical solution. In other words, you're not getting a single constant. Okay, so when you see integrals written with this symbol, this is an indefinite integral because, yes, we end up with x squared over 2. That is correct, but it's not a specific amount. It's not a constant. If we need that constant amount, we have to specify the interval over which this integral is being evaluated. So in other words, this integral implies that I'm taking the entire function over its entire domain and coming up with this result. But what if I'm not interested in that? What if, for example, let's try this one. So I can integrate over the entire curve, and I'll end up with x cubed over 3 plus c. But what if I'm really only interested in the area between, let's say, 1 and 5? What will happen is that when I evaluate it, I will come up with a very specific result. It will be a constant that represents the area under this curve between the points 1 and 5. And the way I express that with my integration formula, or symbol, I should say, is I'm going to add the lower and the upper limits to my integrals symbol. And so what will be different now is that when I find my integral, I can evaluate it and provide it with a numerical result. a constant like 3 or 7 or something like that. This type of integral, where I'm looking over a specific range of values, is now called a definite integral. And I'll show you how to actually solve for this thing. But you're basically doing the same approach, but you're now applying the endpoints to your final result to come up with a numerical value that represents the area under this curve. Okay, so that's where we're going. That will sometimes you only need the indefinite integral, and sometimes you need the results from a definite integral. It depends on what you're trying to accomplish. So the reason why I mention all that is because when you look at this graph, you'll see that this is a definite integral. What I'm looking for is specifically the area under this function between the points A and B. And so I need a numerical value, a constant of some kind, to give me the area. Okay, in other words, I need more than just a formula. I need the actual numerical value of this area. Now, what we're going to do, as I started to say before, in fact, why don't I do this? Why don't I copy this so I can write on it without ruining it? And our strategy, we'll say, well, you know, why don't we try this? Let's put some rectangles in here. We're going to choose a width for all of our rectangles. They all have to have the same width. What will be different for each rectangle is its height. They will reach up to the curve and touch it at one point. Now, this graph isn't working out that great. Let me show you another one so you can see it a little better. Let's try this one. So let's say I'm interested in this range in here. So the rectangles, the idea is that the rectangles will touch the curve at one point. Okay. So I think it's easier to see it in this example. The problem you notice is that the rectangles are touching the curve, but the tops are flat. So that means that while on the left-hand side of each rectangle, we may be reaching the curve exactly, on the right-hand side, we're not. And so there's a bunch of blank space in here that we're missing. Let me see if I can, I'll try to fill it in a little bit. Here, here, and here, and here. So in other words, you can see already there's going to be some inaccuracy. What do I do about it? Well, it turns out if the widths of these rectangles were smaller, let's say that the rectangles were half as wide as they are here, you'd still get those blank spaces, but they'd be smaller than you're seeing here. And in fact, if I keep shrinking up the widths of these rectangles in the limit, they will actually precisely match the curve. But that means that the width of the rectangles is converging to 0. Okay, so in other words, this is only the limiting case. If I allow the widths of the rectangles to get smaller and smaller and converge to 0, the sum of those rectangles' areas will tell me the precise area under this curve. And so the definite integral is designed to do exactly that for us. what it's doing, and then this is why I said earlier that it represents, you can thought of as an infinite sum, because if we keep shrinking up the size of the rectangles, eventually there will be an infinite number of them under that curve. So this integral is an infinite sum of areas of rectangles. Okay, so this is where we're going with this stuff. And we're going to see numerically how to do this, but just once or twice, and so that we truly understand what an integral is. And then after that, we can focus all of our attention on the rules. Okay, anyway, so this is going to get a little deep for a while. So here's what we're going to do. We're going to take a fun detour here. I'm sure you've seen this before, but the Greek letter sigma is frequently used to represent sums or summation. Sometimes it's called the summation operator. We're going to use it quite a bit here in our discussion about integrals. So what we want to do here is review how this thing works. Okay. So it basically tells you that you're adding some numbers together. That's really all that it is. Now, because we need to keep track of what numbers are being added together, the summation operator often has an index attached to it. So what you're seeing here, you've got I as an index. Every number that we want to add together has its own unique index. So like if you're looking at rectangles, you might have something like this going on. These are the bases of the rectangles. For some function or other. And the n represents the number of values that you're adding together. So what you're seeing here is a shorthand notation for this. Oh, yes. Now, it's possible you've seen this before. It's possible that you haven't, or it's possible you haven't seen it in a long time. It's a very compact way of expressing a sum of n terms. Now, by the way, this notation is more general than it looks. The index doesn't have to start with 1, although it often does. And if you notice, we're assuming that the index increases 1 at a time, from 1 to 2 to 3 to 4. You can actually change that if there's a good reason. You can have, let's say, 2, 4, 6, 8, 10, or something like that. But normally we just start at 1 or 0, maybe. And then we allow the index to increase 1 at a time until we get to n. If not, it has to specifically tell you that it's doing something different. Okay. So here's a quick and simple example. What if I've observed the temperatures in Minnesota on the first 5 days in January? Okay, that looks about right, doesn't it? I think so. I've got 5 terms. I want to add them up for some reason. So what I've got is xi, the sum all the way up to n. Since we have 5 elements, I add them up and I end up with a 10. Okay, so this is x1, the first day's temperature, x2, x3, x4, and x5. Actually, over here, I could have written this with a 5 because we know how many elements there are, but that's fine. So the summation operator very simply says, add up all those temperatures and you end up with 10. Now, what you're seeing here is the summation of the x's, but we can actually add up functions of x too. And in fact, we often will. So let me show you some simple examples of this. What if for some reason I'm not interested in the sum of the temperatures, but the sum of the squared temperatures? This is what the notation would look like. I've replaced xi with xi squared. And that says, listen, go through all of these, add up the squares, and at the end, in this case, you can see you'll end up with 40. Okay, so notice the key here is that you're squaring the terms and then you add them up. Now, you never know when you might need something like this. You might say, well, this is, when are we ever going to need this? But it turns out that for certain applications, you may need something like this. You see this all the time in statistics, for example. On the other hand, what if I want to square the sum of the terms? If you notice, this time the square is on the outside. It's not attached to the x, it's attached to the sum itself. What that's telling me is that I'm going to add up all these numbers first, and only when that's done will I square them. Square the sum, that is, not the terms, the sum. So if you notice, before, when I squared the terms, I got a sum of 40. But here, when I sum first and then do the squaring, I ended up with 100. They're not equal to each other. They mean something different. Here's something that proves to be useful. You might not think so, but what if I want to take all the temperatures and subtract some constant amount and then square the results? So again, this is something you might see in statistics. And there's nothing to stop us from doing that. We just have to understand what the symbols are telling us to do. So here, what you have to do is within the parentheses, subtract the constant in each case. Then you square the difference. And then at the end, you add them up. Okay, so it's a three-part process. All right. So let's see how that would work with the temperature data. What if I, for some reason, need to subtract 3 from each temperature and then square the results before I add them up? Okay, well, you'll go through the list of, remember the elements were 2. This was x1, x2, x3. X4 and X5. In each case, I'm subtracting 3, and then I square the result, and then finally at the end, I add them up. So there's all kinds of things I can do with the summation notation. I can apply to, in principle, it can be any function of x that I need. So it's a very powerful and flexible notation. Okay, well, it's getting, all right, let's look at some of the rules. I'll tell you what, let's look at a few of the basic rules. Before we stop, there's a few that we can go over. In the most general possible terms, what would happen if I wanted to apply this to a constant c? Well, that means I'm adding c n times, which means that my sum must be n times c. So let's say, for example, I had this is telling me to add 6 4 times, which I could rewrite as 4 times 6. This is n. This is my constant. And so it does work. So if you run across the summation applied to a constant, then you just multiply it by the number in terms. Or here's another example, the one that I put in the slides. You can see that here we're adding 3 5 times. And so I can just as easily calculate it as 5 times 3 and end up with 15. And also, like with the integrals, you can factor that c out of there. Like, for example, here, what if I want to take my temperature data and sum not the actual temperatures, but sum 2 times the temperatures for some reason? Well, what you're doing is you're basically multiplying each one by 2 and then adding them up. But what you're also doing and since we know that that sum is 10, what you can just do is say, oh, then there must be 20. Well, that's kind of cool. Now here, these are pretty straightforward. Sum, if I'm trying to calculate the sum of a sum, then I can break it up into 2 separate sums. If I'm trying to calculate the sum of a difference, then I can break it up into the difference of those 2 sums. Just like with the integrals. Remember, the integrals are themselves just infinite sums. So anything that applies to the integrals has to apply here. Now, this is an interesting one. What's going on here? Let's just say that let's just make up some specific values. The terms, here it's A instead of N. Actually, it doesn't really matter what letter you use here. Suppose you had something like this. These are your terms. What this is saying is that the sum of those 5 can be broken up into 2 smaller groups. You could say, for example, go from 1 to 3, and then go from 4 to 5. And you'll just get the same thing. So in other words, the sum of the first 3 is 9. The sum of these 2 is 5. And so you end up with 14. Now, in a case like this, this did not do you any good, but sometimes you might find that it's easier to break this up into different components. Or else if you already have them split up like that, it's nice to know that you can put them back together, so to speak. All right. Now it starts getting intense. So, all right, why don't we stop right here? And when we come back again, we'll carry on with this discussion about integrals. Now, we haven't, as you can see, started to actually formally define the integrals. This was a bit of a detour to make sure we have this background because as you'll see, we'll be treating the integral as an infinite sum of areas of rectangles. So we do need to be comfortable with this notation before we get to that point. So I think, and plus, you never know when this stuff might come in handy. Like I said, you'll see this all the time in statistics if you take that. Or if you're taking a computer science course, it might come in handy. So, all right, I think we've done enough for now. So remember, keep working on that midterm. And don't forget, number 7 is not going to be counted. But, keep going with that. And then we'll see each other again on Monday, and we'll carry on with our discussion about integrals. And I think that's the whole chapter. I think the whole chapter is about integration. So that's going to take a while to get through. All right. So I guess if there's no questions, I'll see you all next time.
Thanks, Professor. Have a good night.
Okay. You're welcome. All right. Good night.